Welcome to our lecture on hotspot volcanism. Most volcanoes form at the edges of tectonic plates, but hotspots are rebels. They usually pop up right in the middle of a plate. We will explore how these abnormally hot centers in the mantle create massive volcanic features far from plate boundaries, with a few exceptions like Iceland and Afar, which sit on divergent boundaries. The driving force behind hotspot volcanism is something called a mantle plume. Imagine a convection current of abnormally hot magma rising from deep within the Earth, right at the core mantle boundary. Unlike massive convection cells that shift around, these plumes stay relatively fixed in place. They look a bit like a mushroom with a long, narrow tail feeding a bulbous head that expands as it rises, eventually forcing its way into the upper mantle as a dome-like intrusion called a diapir. So, what happens when this massive plume head hits the bottom of the rigid lithosphere? It flattens out. The drop in pressure causes widespread decompression melting, generating enormous volumes of basaltic magma. This magma does not just form a single mountain, it erupts through a series of cracks or fissures, flooding the surface to create large igneous provinces. These are massive accumulations of flood basalts that can cover thousands of square kilometers, like the Siberian traps or the Deccan traps. These massive flood basalt events are not just geological curiosities, they have profoundly impacted life on Earth. The sheer volume of lava and volcanic ash can trigger long-lasting climate change, sometimes even small ice ages. For instance, the formation of the Siberian traps 250 million years ago coincided with the devastating Permian-Triassic extinction. Similarly, the Deccan traps formed about 66 million years ago, adding severe environmental stress right around the time the dinosaurs went extinct during the Cretaceous-Paleogene event. When a mantle plume provides a steady, continuous supply of heat to a fixed location, we call that a hotspot. The intense heat melts the rock at the base of the lithosphere. This highly pressurized magma then forces its way up through fractures in the Earth's crust, eventually erupting onto the surface to build massive hotspot volcanoes, such as Mount Mauna Kea in Hawaii. But remember, the tectonic plate above the hotspot is constantly moving. Eventually, the active volcano is carried away from its heat source and gets cut off. Without fresh magma, it goes extinct. As the rock cools, it becomes denser, causing the island to slowly sink and erode into a seamount. Meanwhile, a brand new volcano begins to form directly over the hotspot. This continuous cycle creates a long chain of volcanoes that perfectly tracks the direction of the plate's motion. The most famous example of this process is the Hawaiian island chain. If you look at a map, you can see a clear age progression. The youngest, active islands are right over the hotspot at present-day Hawaii. As you move northwest along the chain, the islands get progressively older, more eroded, and eventually submerge completely as seamounts, stretching all the way to the Aleutian Trench. Another fascinating trail is left by the Reunion hotspot in the Indian Ocean. It started with a massive eruption 66 million years ago that created the Deccan traps in India. As the Indian plate drifted north, the hotspot punched through repeatedly, leaving a trail of volcanic islands and underwater plateaus. This trail includes the Chagos-Laccadive Ridge, which the Maldives and Lakshadweep are part of, and the Mascarene Plateau, ending at the currently active Reunion Island. Mantle plumes do not just build islands, they can actually tear continents apart. As the plume rises and diverges just below the lithosphere, it exerts immense extensional or tensile stress on the plate above. This outward pulling force causes the rigid crust to stretch, then out, and eventually rupture, forming a deep rift valley. A perfect modern example of this rifting is the Afar hotspot in East Africa. The mantle plume beneath this region has ruptured the crust, creating the Afar triple junction. Here, the Nubian, Somalian, and Arabian tectonic plates are all being actively pushed away from a central point. This divergence is actively splitting the African continent and has formed major features like the Red Sea Rift and the East African Rift. Before a plume completely tears a plate apart, it often causes massive uplift, known as epirogenic movement. As the plume reaches the crust and spreads out laterally, it acts like a giant hydraulic jack, doming up vast zones of the Earth's surface. The Ethiopian highlands are a prime example. Before the massive flood basalts erupted and the Rift Valley opened, the underlying mantle plume uplifted a massive dome of ancient rock. When a mantle plume develops beneath a thick continental plate, like the Yellowstone hotspot in North America, we see severe crustal thinning. The extensional stress from the diverging plume stretches the continental crust above it, Over time, this thinning weakens the surface, essentially opening the door for the massive, highly pressurized magma chambers below to interact with the surface, setting the stage for a supervolcano. This brings us to the terrifying concept of supervolcanoes. A supervolcano is defined as a volcano capable of erupting more than 1,000 cubic kilometers of magma in a single event. They form when a colossal volume of magma accumulates under a lithospheric plate, but cannot easily break through. Over thousands of years, the pressure relentlessly builds up until the rock above simply cannot contain it anymore, resulting in a catastrophic eruption. Earth has seen over 40 of these super eruptions, like the Toba eruption in Indonesia 74,000 years ago. The disaster potential is staggering. A super eruption can cause regional extinctions instantly. Worse, the sheer volume of ash can blanket entire continents, while sulfur aerosols ejected into the stratosphere reflect sunlight away from the Earth. This can plunge the planet into a severe, years-long global winter, drastically altering the climate. Now let us look at how these massive igneous rocks fit into the broader rock cycle. Moving right along into the materials that make up the Earth's crust, let's look at rocks. A rock is simply an aggregate of one or more minerals held together by chemical bonds. While there are many minerals out there, feldspar and quartz are by far the most common ones you will find in rocks. And if you ever decide to study these formations professionally, you would be engaging in petrology, which is the scientific study of rocks. Based on how they actually form, geologists classify rocks into three major groups. First, we have igneous rocks, which solidify directly from molten magma and lava. Second are sedimentary rocks, which are created when fragments of older rocks are deposited and compacted over time. And third, we have metamorphic rocks, which are existing rocks that have been fundamentally changed or recrystallized by intense heat and pressure. Let's start with igneous rocks, which are often called primary rocks because they form the basis for the other types. They're created through the solidification of magma, which is molten rock trapped below the surface, or lava, which is molten rock that has erupted above the surface. Because they originate in extremely high-temperature environments, igneous rocks are unfossiliferous, meaning any organic matter would be completely incinerated before a fossil could form. Common examples include granite, gabbro, and basalt. Igneous rocks are further divided based on where they cool. When magma never reaches the surface and instead cools slowly at great depths, it forms intrusive or plutonic rocks. This slow cooling process allows very large mineral grains to develop. We usually only see these rocks, like granite, on the Earth's surface after millions of years of geological uplift and the erosion of the layers above them. As you can see in the diagram, these deep formations take shapes known as batholiths, sills, and dikes. Conversely, extrusive igneous rocks, or volcanic rocks, form when magma cools suddenly just below the surface, or when lava cools rapidly above it. Because the cooling happens so fast, large crystals don't have time to form. This results in rocks with small, smooth, fine grains. Basalt is a classic example, and the massive Deccan traps in India are entirely of basaltic origin. These basic rocks are rich in heavy oxides like iron and magnesium, which makes them quite dense and dark in color. There is also a middle ground known as hypoabyssal or dike rocks. These occupy an intermediate position, both physically and structurally, between the deep-seated plutonic bodies and the surface lava flows. Because their cooling rate is somewhere in between, they develop a semi-crystalline structure. We can also classify igneous rocks by their chemical composition, specifically their silica content. Acidic rocks are characterized by a very high silica content, up to 80%. Because they lack heavier minerals like iron, they are lighter in color and less dense. However, they are incredibly hard and resistant to weathering, making up the Ciel portion of the continental crust. Because acidic magma is thick and viscous, it cools fast and doesn't flow very far, which is why it typically forms high, steep mountains. On the other end of the spectrum are basic igneous rocks. These are poor in silica, but rich in magnesia and other heavy elements, which gives them a distinctively dark color. They aren't as hard as acidic rocks, so they weather more easily. A key feature of basic basaltic magma is that it is highly fluid. It flows and spreads over vast distances before slowly cooling, which is exactly how massive, flat volcanic plateaus are formed. Igneous rocks hold immense economic value. Since magma is the primary source of metal ores, igneous rocks are where we find crucial resources like iron, copper, gold, diamond, and platinum. Additionally, as basalt cools, escaping gases leave behind bubbles called amygdalus, which often fill with beautiful crystallized minerals. And of course, rocks like granite are highly prized as building materials because of their durability and beautiful natural shades. Now, let's examine the second major group, sedimentary rocks. These are formed through a process called lithification, which is the consolidation and compaction of loose sediments. These sediments come from the weathering and erosion of older rocks. Over time, they settle and compact into distinct layers, or strata. We even have specific names based on how the sediment was moved. Tillite is deposited by glacial ice, while loess is deposited by the wind. Interestingly, while sedimentary rocks cover about 75% of the Earth's surface area, they only make up about 5% of the crust's total volume. This is because they exist almost exclusively as a thin veneer on the very top layer of the crust. Depending on exactly how they form, we classify them into 3 categories: mechanically formed, organically formed, and chemically formed. Mechanically formed sedimentary rocks are created by physical agents like rivers, wind, or ocean currents moving rock fragments around. Within this category, we have arenaceous rocks, like sandstone, which are made of large, sand-like particles. They are highly porous, making them excellent underground reservoirs for water and petroleum. In contrast, argillaceous rocks, like shale, are made of fine clay. They are soft and mostly impermeable, meaning water cannot easily pass through them. Next, we have chemically formed sedimentary rocks. These occur when water that is rich in dissolved minerals evaporates, leaving the solid minerals behind. A beautiful example of this happens in underground limestone caves. As mineral-rich water drips and evaporates, it builds up hanging formations called stalactites and ground formations called stalagmites. The third type is organically formed sedimentary rocks. These are fascinating because they are made from the actual remains of ancient plants and animals. When these organic remains are buried under heavy sediments, heat and pressure slowly change their composition. If the rock is mostly made of calcium from shells and bones, it's a calcareous rock, like chalk or limestone. If it's mostly carbon from ancient plant matter, it becomes a carbonaceous rock, like coal. To summarize their key traits, sedimentary rocks are highly stratified, meaning they are built in distinct layers. They are generally porous, allowing water to percolate through. Most importantly, they are fossiliferous. Because they form gently at the surface, rather than in fiery magma, they preserve the remains of plants and animals perfectly. This makes sedimentary rocks the ultimate history book of the Earth, holding our most informative geological records. Looking at India specifically, sedimentary rocks are widely distributed and shape much of the landscape. The massive Indo-Gangetic Plain is made of sedimentary alluvial deposits of loam and clay. You'll find vast stretches of sandstone across Madhya Pradesh and Rajasthan. The Vindhyan highlands are built of sandstones, shales, and limestones. And crucially, India's major coal deposits are found in the sedimentary basins of the Damodar, Mahanadi, and Godavari rivers. Economically, sedimentary rocks are incredibly important. While they might not have the raw precious metals of igneous rocks, they are the exclusive source of fossil fuels like coal and petroleum. They also provide hematite iron ore, phosphates for agriculture, and the raw materials needed for the cement industry. Furthermore, the weathering of sedimentary rocks yields some of the richest, most fertile agricultural soils on the planet. Let's test our understanding with a past exam question. Look at these 4 statements about sedimentary rocks. We know they form at the surface via water and wind, so statement 1 is true. They definitely form from the weathering of older rocks, making statement 2 true. We just discussed how they are fossiliferous, so 3 is true. And they are stratified, meaning they occur in layers, so 4 is true. Therefore, the correct answer is D. All 4 statements are correct. Our third major rock group is metamorphic rocks. The word metamorphic literally means change of form. This happens when an existing rock undergoes severe pressure, volume, and temperature changes, causing the minerals inside it to completely recrystallize and reorganize. During this intense process, minerals often align themselves into distinct layers or lines, a feature called foliation. If different minerals separate into alternating light and dark layers, we call it banding. What actually causes a rock to undergo metamorphism? There are 3 primary drivers. First are orogenic, or mountain-building movements, where the crust is violently folded and warped. Second is lava inflow. When magma pushes up through the crust, it bakes and crushes the surrounding rocks. Finally, general geodynamic forces, like the slow grinding collision of tectonic plates, provide the massive pressure needed to alter rocks on a continental scale. When heat is the primary driver of change, we call it thermal metamorphism. The intense temperatures literally bake the original rock into something new. For example, ordinary sandstone is baked into ultra-hard quartzite, and limestone is transformed into beautiful marble. In fact, a magmatic intrusion deep in the past baked the rocks at the top of the Himalayas, which is why the very peak of Mount Everest actually consists of metamorphosed limestone. On the other hand, when high pressure is the dominant force, it results in dynamic metamorphism. When you combine this crushing directed pressure with high heat, it's called dynamo-thermal metamorphism. This combination is incredibly powerful, leading to a complete recrystallization of the rock. Under these forces, a tough igneous rock like granite is crushed and stretched into banded gneiss, while soft clay and shale are compressed into schist. Here is a handy reference table showing common metamorphic transformations. Notice how the original rock and the specific factor, whether heat or pressure, determine the final result. Granite under pressure becomes gneiss. Sandstone under heat becomes quartzite. And look at coal. Under intense heat, it first becomes hard anthracite coal, and with even more heat, it transforms entirely into graphite. In India, metamorphic rocks are found in several key regions. Gneisses and schists are widespread across the Himalayas and central states. Hard quartzite is found around Rajasthan, MP, and Delhi. Rajasthan is particularly famous for its high-quality marble, found in places like Jaipur and Jodhpur. Slate, historically used for roofing and writing boards, is mined in Haryana and Himachal Pradesh, while graphite deposits are located in Orissa and Andhra Pradesh. Here is another quick knowledge check from a past exam. Quartzite is metamorphosed from which rock? As we just saw in our transformation table, when sandstone is subjected to intense thermal metamorphism, its quartz grains fuse together. Therefore, the correct answer is C, sandstone. All these rocks we've discussed do not exist in isolation. They are part of the rock cycle. This is a continuous, millions of years long process where old rocks are constantly transformed into new ones. Igneous rocks break down to form sedimentary rocks, or get buried to become metamorphic rocks. Eventually, any of these crustal rocks can be pushed deep into the Earth's mantle through tectonic subduction, where they melt back into magma, ready to erupt and start the cycle all over again. This diagram beautifully illustrates that continuous loop. You can trace the pathways. Magma crystallizes into igneous rock, which is then uplifted, weathered, and eroded. Those sediments are transported, deposited, and compacted into sedimentary rock. If that rock is buried deep enough, high temperatures and pressure turn it into metamorphic rock. And if it goes even deeper, it melts back into magma. To wrap up our discussion on rocks, we must look at the specific minerals that actually build them. Feldspar is incredibly abundant, making up about half of the Earth's crust, and is widely used in ceramics. Quartz, made of silicon and oxygen, forms distinct hexagonal crystals and is crucial in electronics like radios. We also have bauxite, which is the primary ore we mine to get aluminum, and cinnabar, a brownish mineral that is our main source of mercury. Continuing with important minerals, we have dolomite, a carbonate used heavily in the cement and steel industries. Gypsum is another vital mineral, essential for making fertilizer and cement. And when it comes to iron, the two most important minerals are hematite, which is a red iron ore, and magnetite, which is a black iron oxide. Finally, let's look at a few more key minerals. Amphiboly makes up about 7% of the crust and is used in the asbestos industry. Mica is highly heat-resistant and is used in electrical instruments. Olivine forms beautiful greenish crystals, often used in jewelry, while pyroxene is notable for being commonly found in meteorites from space. Understanding these foundational rocks and minerals is critical because they set the stage for the massive tectonic forces we will explore next, such as earthquakes. An earthquake is fundamentally a sudden shaking or trembling of the Earth's surface. This happens when seismic waves are generated by a sudden release of energy, usually in the Earth's crust or upper mantle. The exact underground point where this energy is released is called the focus or hypocenter. The point on the surface directly above the focus is the epicenter, which is the first place to feel the waves. We also map these events using isoseismic lines, which connect all points on the surface that experience the exact same intensity of shaking. Earthquakes rarely happen as a single isolated event. Often, a major shallow focus earthquake is followed by many smaller tremors known as aftershocks as the Earth's crust settles. Sometimes a mild earthquake, called a foreshock, actually precedes the violent shaking of the main event. In some regions, you might experience large numbers of small earthquakes over several months without any major quake occurring. These are known as earthquake swarms. Swarms are highly associated with volcanic activity and can actually serve as markers, tracking the location of flowing magma deep underground. Moving on to what actually causes these massive releases of energy. The immediate cause of most shallow earthquakes is the sudden release of stress along a fault rupture, which is essentially a crack in the Earth's crust. This stress builds up because rocks deep inside the Earth are constantly changing in volume and density due to intense temperature and pressure. When the rock finally snaps or shifts, energy is released. A simple rule of thumb here is that the longer and wider the faulted area, the larger the resulting earthquake's magnitude will be. The type of fault heavily influences the size of the rupture. The longest earthquake ruptures occur along thrust or reverse faults, which are found at convergent plate boundaries, where plates collide. These ruptures can stretch for approximately 1,000 kilometers. On the other hand, strike-slip faults, found at transform boundaries, where plates slide past one another, produce ruptures about half to one-third that size. Finally, normal faults, which occur at divergent boundaries, where plates pull apart, generally produce the shortest fault ruptures. Because fault types are tied to tectonic plate boundaries, we can predict maximum magnitudes based on the boundary type. Slipping land along normal faults at divergent boundaries generally causes earthquakes of less than magnitude 7. Strike-slip faults, like the famous San Andreas Fault, where the Pacific and North American plates slide horizontally, can produce major earthquakes up to magnitude 8. But the most powerful earthquakes, known as megathrust earthquakes, happen at convergent boundaries with reverse faults. These occur at subduction zones, where one plate is forced under another, producing quakes of magnitude 8 or higher, like the devastating 2004 Indian Ocean earthquake. Fascinated? Volcanic activity is another significant trigger. While earthquakes of volcanic origin are generally less severe and more localized than tectonic ones, they are crucial to monitor. They are caused by the release of elastic strain energy from both tectonic faults and the physical movement of magma pushing through the rock. Because of this, these quakes act as an early warning system for volcanic eruptions, famously preceding the 1980 eruption of Mount St. Helens. Geographically, there is a strong overlap between volcanoes and earthquakes, especially along the Pacific Ring of Fire. It is not just nature at work. Humans can induce earthquakes as well. Human-induced earthquakes are typically minor tremors, but they are directly caused by our activities altering the stress in the Earth's crust. Major culprits include deep mining operations, large-scale petroleum extraction, the creation of massive artificial lakes or reservoirs, and the detonation of underground nuclear tests. All of these activities either remove mass, add massive weight, or send massive shockwaves through the crust. Let us look closer at reservoir-induced seismicity. When we build a large, deep artificial lake, the immense pressure from that column of water alters the stress along existing underground faults. Furthermore, water percolates down, weakening the soil structure and literally lubricating the fault lines. The cycle of loading and unloading water can trigger a sudden movement. A tragic example is the 6.3 magnitude Koynagar earthquake in 1967 near a dam in Maharashtra. Similarly, some geologists believe the filling of the Zipingpu Dam may have triggered the catastrophic 2008 Sichuan earthquake. Earthquakes can occur anywhere from the surface down to about 700 kilometers deep. Scientists divide this range into 3 zones. Shallow earthquakes occur between 0 and 70 kilometers deep, within the outer crust. Intermediate ones happen between 70 and 300 kilometers, and deep earthquakes occur from 300 to 700 kilometers down, in deeper subduction zones. Interestingly, shallow earthquakes account for the vast majority of seismic energy released globally, about 70 to 85%, while deep earthquakes contribute only 3 to 5%. An earthquake's destructive force depends heavily on its depth, not just the energy released. Consider August 24, 2016. A 6.2 magnitude earthquake hit central Italy, originating just 10 kilometers underground. Because it was so shallow, the shaking at the surface was violent, killing about 300 people. On that exact same day, a significantly stronger 6.8 magnitude quake hit Myanmar. However, it originated 84 kilometers deep. Because the energy had more distance to dissipate before reaching the surface, it resulted in very few casualties. Let us examine shallow focus earthquakes, often called crustal earthquakes, in more detail. The great majority of all earthquakes fall into this category. While they occur quite frequently, most are of smaller magnitudes, usually between 1 and 5, and many happen unnoticed along submarine ridges. However, when a shallow quake does strike a populated area, it can cause relatively greater surface damage than a deep quake of the exact same magnitude. This is because the entire energy of the quake is concentrated and directed toward a very small area on the surface. Conversely, deep focus earthquakes occur deeper than 70 kilometers. They commonly happen in patterns called Benioff zones, which indicate a subducting slab of rock. Because they are triggered by the intense collision between plates, they are also known as intraplate earthquakes, and often happen as huge quakes with magnitudes between 6 and 8. But despite this massive energy release, they rarely cause much destruction. The foci are so deep that the energy dissipates over a very wide area before reaching us. The deepest ever recorded was an incredible 735.8 kilometers deep in Vanuatu. The specific area where these deep quakes happen is called the Wadati-Benioff zone. This is a zone of subduction where one plate is being dragged down into the mantle. The differential motion along this zone produces numerous earthquakes, and because this is a convergent boundary, it is home to the most powerful earthquakes on Earth. The quakes here can be produced either by slipping along the main subduction thrust fault, like in the Himalayas, or by slipping on faults within the actual downgoing plate itself. Where do most of these earthquakes happen? Earth's major earthquakes occur mainly in belts that coincide with the margins of tectonic plates. The most dominant of these is the Circum-Pacific Belt, popularly dubbed the Pacific Ring of Fire. This single belt accounts for roughly 68% of all earthquakes globally. It affects heavily populated coastal regions around the Pacific Ocean, including New Zealand, Japan, Alaska, and the western coasts of North and South America, and is heavily associated with intense volcanic activity. The second major belt is the Alpine Belt, which accounts for about 15% of the world's total earthquake energy. This mid-world mountain belt extends from the Mediterranean Sea, across the Alpine and Caucasus ranges, all the way through the Himalayan mountains. Beyond these two main belts, there are striking connected lines of seismic activity that run mainly along the mid-oceanic ridges in the Arctic, Atlantic, and Indian Oceans, as well as along the massive continental rift valleys of East Africa. To measure the strength or energy released by these quakes, Charles F. Richter developed the Richter magnitude scale in the 1930s. However, because it is only effective for regional quakes up to magnitude 5, seismologists today use the moment magnitude scale for larger events, though the public still commonly calls it the Richter scale. Both scales are logarithmic. This is crucial to understand. An increase of just one step, say from a 5 to a 6, means 32 times more energy is released. An increase of 2 steps means a massive 1,000 times increase in energy. Let us break down what these numbers actually feel like. Magnitudes between 1.0 and 2.9 are micro or minor quakes. They happen millions of times a year and are rarely felt. In the 3.0 to 3.9 range, you might notice indoor objects shaking, but damage is rare. A light quake in the 4.0 range is felt by most people and might knock objects off shelves. Once we reach the 5.0 to 5.9 moderate range, which happens about 1,000 times a year, poorly constructed buildings can suffer severe damage, though well-built structures usually survive with slight damage. Seriously, moving up the scale, the danger increases exponentially. A strong quake in the 6.0 range causes moderate to severe damage, even to well-built structures. Major quakes in the 7.0 range happen 10 to 20 times a year and can cause buildings to completely collapse, with damage spreading up to 250 kilometers from the epicenter. Great earthquakes of 8.0 and above happen about once a year, destroying sturdy structures across massive regions. And a 9.0 or greater, occurring perhaps once every few decades, cause near total destruction and can permanently alter the ground topography. Looking at the historical record, the most powerful earthquake ever recorded was the 1960 Valdivia earthquake in Chile, an undersea megathrust event estimated between 9.4 and 9.6 magnitude. Second is the 1964 Alaska earthquake at 9.2. Third is the devastating 2004 Indian Ocean earthquake. This 9.1 to 9.3 magnitude rupture created 30-meter-high tsunamis, caused over 227,000 casualties, and released so much energy it slightly altered the Earth's rotation. Fourth is the 2011 Tohoku earthquake in Japan, a 9.1 magnitude event that triggered a massive tsunami and the Fukushima nuclear disaster. Other notable earthquakes stand out for their unique impacts. The 1556 Shanxi earthquake in China was an 8.0 magnitude event, but it remains the deadliest in recorded history, with over 800,000 fatalities, mostly because people lived in artificial caves carved into soft Loess cliffs that collapsed. In India, the 1819 Rann of Kutch earthquake caused such massive ground uplift that it formed an 80-kilometer-long natural dam, locally called the Allah Bund, or Dam of God. Centuries later, the 2001 Kajart earthquake reactivated these same ancient rift faults, tragically killing up to 20,000 people. To prepare for these disasters, the National Disaster Management Authority maps seismic vulnerability. Their latest map reveals that nearly 59% of India's land area is prone to moderate or severe earthquakes. The country is divided into 4 active zones. Zone 5 represents the highest risk, covering the northeast, Jammu and Kashmir, Uttarakhand, and parts of Himachal Pradesh. Zone 4 includes the Delhi National Capital Region. Zone 3 covers central India with moderate risk, while Zone 2 covers most of the south, representing the lowest, though not zero, seismic danger. The Delhi NCR region falls into Zone 4 and has been witnessing many low-intensity earthquakes recently. This is a concerning sign that a major earthquake may be due. Delhi sits very close to multiple active tectonic faults, including the Mahendragarh-Dehradun, Sona, and Mathura faults. Furthermore, there is a 500-kilometer-long central Himalayan seismic gap to the northwest. A seismic gap is a portion of a fault that hasn't ruptured in a long time, in this case 200 to 500 years. This indicates a massive accumulation of strain that could eventually release in one large burst. Moving to Zone 5, Northeast India is a highly fragile and earthquake-prone region. Its high seismicity is due to a very complex tectonic juxtaposition. Here, the east-west trending Himalayan mountains meet the north-south trending Arakan-Yoma belt. This intense squeezing of the crust creates numerous major fault lines in the region, most notably the Pochu Fault, the Kopili Fault, and the Jiali Fault, making the entire northeast highly vulnerable to severe seismic activity.
Let us look specifically at the Kopili Fault zone. This is a massive tectonic depression, 300 kilometers long and 50 kilometers wide, extending from Manipur up to the tri-junction of Bhutan, Arunachal Pradesh, and Assam. It is filled with alluvium from the Kopili River. This fault sits very close to the Himalayan frontal thrust, which is the actual tectonic boundary where the Indian plate is actively subducting beneath the Eurasian plate. This ongoing collision is exactly why this area is classified under the highest seismic hazard zone, V.
When these massive forces are finally released, the effects are devastating. The most immediate effects are shaking and ground rupture. The physical cracking of the earth along a fault is a major risk for large engineering structures like dams, bridges, and nuclear power stations. In mountainous regions, this violent shaking often produces severe slope instability, triggering massive landslides and avalanches that can bury roads and entire villages, acting as a major secondary geological hazard. Beyond the shaking, earthquakes trigger deadly chain reactions. Fires are incredibly common, sparked by ruptured gas lines and downed electrical wires. In fact, during the famous 1906 San Francisco earthquake, more deaths were caused by the ensuing fire than by the earthquake itself. Another bizarre but destructive effect is soil liquefaction. This occurs when violent shaking causes water-saturated soil to temporarily lose its structural strength and behave like a liquid. When this happens, massive rigid structures like buildings and bridges can simply tilt over or sink into the ground. Finally, earthquakes can unleash massive water hazards. Undersea megathrust earthquakes can abruptly displace enormous volumes of water, generating tsunamis, long-wavelength, high-speed sea waves that can devastate coastlines thousands of miles away. Inland, earthquakes can cause severe flooding. This happens either directly, when man-made dams are ruptured by the shaking, or indirectly, when earthquake-triggered landslides block rivers, creating unstable natural dams that eventually collapse and flood the valleys below. To wrap up our discussion on earthquakes, remember that these are sudden, massive releases of energy, primarily driven by the shifting of tectonic plates along fault lines. The destructive power we experience on the surface is heavily dictated by how deep the earthquake originates and the specific type of fault involved. We must also recognize that human activities can induce seismic events. Ultimately, understanding these mechanisms is vital because the secondary effects, like tsunamis, fires, and landslides, often prove far more devastating than the shaking itself.